Okay, I'm going to show you in this video how the Taylor series is used to extrapolate a function where you know a value at a certain location and you want to use the Taylor series to extrapolate and get a value at the next location down the road. And so here's Taylor series written out. Um, and this is written out to fourth order in delta x because we've got the first four terms here there, and there, and we're truncating the series here and saying everything with every term that has delta x to the fourth or greater, we're going to not use. Okay, so this will give us an approximate value for f at a plus delta x. And so here's what we mean by that. This will be our function, 1 minus e to the minus 2x, and a plot of that looks somewhat like this. And if we say that this point here is point A, and this distance here is delta x, then this point here is a plus delta x, and that point there is f at a, and right there, that's the point that we're after, that value right there, f a plus delta x. Okay, so that's the value here on the left hand side, and on the right hand side we have f evaluated at a, the first derivative at a, second derivative at a, and so on. Okay, so this is how we would implement it. We would say that f on the left hand side, f at a plus delta x would be f at 1 point, well, actually, before we do that, let me say that in this case, a equals 1 and delta x equals 0.5. So this would be x equals 1 right here, and if delta x is 0.5, that this equals x equals 1.5. So we can substitute into Taylor series to see what this gives us. On the left side, it's the function evaluated at 1.5, and that equals the function evaluated at 1 plus delta x, which is 0.5, times the function evaluated, or the derivative evaluated at 1, plus delta x, which is 0.5 squared over 2, times the second derivative at 1, plus 0.5 cubed over 6 times the third derivative evaluated at 1. And then we truncate the series, and this will give us the result in an approximate form. Okay, so now we need to have these values and this one. Well, we already have f of x, so we can get those values. F prime of x is just simply the first derivative of x, and since we're given that, we just take the derivative, and it's going to be 2e to the minus 2x. The second derivative is equal to minus 4e to the minus 2x, and the third derivative will be 8e to the minus 2x. Okay, so substituting in then, f at 1.5 would be 1 minus e to the minus 3, and that's equal to f at 1, which would be 1 e to the minus 2. That's the first term. And the second term is 0.5 times this value here, times 2e to the minus 2, and since x is 1, we're just left with that. And we have the second term, which would be minus 0.5 squared over 2 times 4e to the minus 2. Okay, that comes from this term here and that term. And then we would get another term here that would be 8 e to the minus 2 times 0.5 cubed divided by 6. That would go right there. Okay, so this now gives us something we can just plug in the calculator and get a set of numbers for the results of this series approximation. And so I did this calculation out, and I'll show you what the results are on this page. So here's what we just wrote out, just in typed form. This is the Taylor series expanded out. These are the derivatives. Here are the terms with the numbers, and then this is the results of the calculation. So on the left hand side, that's the exact value. So that's the exact value right there. This value here, that's the results of, it's just right here, f of 1. And that would be what we would get if we would truncate the series right here and just use this first term. So this would be, this result here would be the result that we would have if the error was proportional to delta x, and that equals 0.86, and so that's going to be just this value right here. Okay, and then if we add the next term to it, that's going to be this term. That's what we would have if the error was proportional to delta x squared. And what that says to do is this right here, that's the derivative, which is the slope right here. So there's the slope. And that slope times delta x, there's delta x, is going to be equal to that. Okay, so right there, that distance right there, that's f prime at x times delta x. Okay, so when I add that, the first and second term together, I get this value right up here. So I'm overshooting. Then when I add the next term, so if I add in the third term is this, and if I look down here, it's that value after I do the calculations. And what this third term says is to take the second derivative, which we can see is negative because this curve has negative curvature. This thing has negative curvature. So we take the second derivative, it's going to be negative, multiplied by delta x divided by 2, and that gives us a negative value. When we add it in, we're going to get a value right here. Okay, if we add that in, and then we add the next term in, which is this term, and when we add that in, we're essentially ignoring everything from here on out. And when we add that term, you can see it's getting smaller. That gives us, when we add all these four terms together, that's going to give us a value right in here that's a little bit overshooting the true value. So what's happening here is that with each additional term that we include, we get a bit closer to the real answer, the true answer. Okay, so what I've done is to compile those results and put them in a table. So here's the set of numbers that we just saw, and these numbers are put in a table right here. So this is K. We had a series, Taylor series included these different terms. So when K equals 0, we had that first term, and when K equals 0, we had that first term, and if we were to truncate it here, then the error term would be delta x, and the error would be, delta x to the n. So n would be 1, 2, 3, 4. Okay, so for each term that we include, we have the error term being proportional to another higher power. Okay, so what I did then in this next column, this column here, is I took this value and then put it there, and then I went and added in that value and put the sum right there, and then I took the sum, added in that value, put that result there, and added that value and put it in there. Okay, and so these then are the sums of a certain number of terms, and they're getting closer and closer to the exact value. This is shown in numbers, the concept that I showed you graphically on the previous page. And then we have the error of the approximation, or the order of the approximation in delta x, and then this is the actual relative error. It says EA, but that should be E sub R, the relative error. And we can see that initially the relative error is minus 0.09, because so it's about 9% low, and then 5% high is the error, and almost 2% low, and then 0.5% high. Okay, so that's what we get for this particular configuration. All right, now the real benefit from doing all of this is going to be to see what happens to the approximation as delta x changes. Okay, so this is all stuff that we just saw on the previous page, and what I'm going to do is I'm going to repeat this by using delta x that's cut in half and then cut in half again. All right, and I'm going to take a look at what the error is. So this column I've brought over here and reproduced it right there. This column is right there, K in Taylor series, and this is the order of the approximation in delta x. So for each one of these terms, I'm going to have error terms that are proportional to delta x, and this is the exponent in delta x. All right, so that I think explains the first three columns. And oops, now let me draw this out and try to sketch what I'm doing. So here's the function, and there's a equals 1, and then I'm not really drawing this to scale, but this is then delta x equals 0.5. So we can think of it conceptually as I know everything about the function here, and I want to predict that value there, and I did that right here. Okay, so now I'm going to cut delta x, and I'm going to do the same thing, but I'm going to say delta x is 0.25. Okay, so now delta x is that, and I want to predict the value right there. Okay, so here it is, and I go and I do the approximation, and then I compare the results to the exact value. So I cut delta x in half. I should be able to do better now because I don't have to extrapolate as far. I don't have to extrapolate half the distance. Okay, so here's what you get. With the first term, so where the order of the approximation is proportional to delta x, then I have that for the error, minus 0.05. And then I include another term in the series, and I get 0.01, and then another term, 0.002, and so on. Okay, so you can see that in each case the error is reduced. Now what I'm going to do is to take the ratio of this error and this error. Okay, so it's the error of delta x to the 0.5 to delta x. Let's see. Yeah, it's going to be delta x at 0.25 to delta x at 0.5. So it looks like 1 over that. Okay, and so you can see right here that for this first term, the error is about, well, the ratio is 0.64. So that error is 64% of that error. And then I do it again, and the ratio is 0.3. I do it again, it's that ratio, 0.125. And I do it again, and the ratio is smaller yet. Okay? So that's the procedure. We're going to repeat it a couple more times. We're going to cut delta x by half again. So now delta x is 0.125. So delta x is now that much. And what I'm going to do is use the Taylor series to try to predict the value at that point. So I'm trying to predict there. And I'm going to go through, calculate the errors, and then I'm going to compare the errors of this set to the errors of the previous set. Okay, and then I get this ratio. And it's 0.57 compared to 0.64 and so on. Okay, and I'm going to do it again. I'm going to cut it in half again and repeat. So there's the errors, and then this is the ratio of the errors. Okay, so now here's kind of the crux of all of this. Ideally, let's take a look up at this approximation right here. So this is proportional. This term here would be proportional to delta x. This is proportional to delta x squared, delta x cubed, and delta x to the fourth. So when I have all of these terms, and I'm truncating it here, I can say that the error is proportional to delta x to the fourth. For this case, if I truncate it right here, I can say that delta x, or the error, is proportional to delta x to the first power. Okay? So what that means is that if I take a look at this first line, that's just using this first term where I say that the error is proportional to delta x to the first power. So if the error is proportional to delta x, then if I cut delta x by half, I should cut the error by half. Okay, and what we see when we did this is at first, when I cut it by half, the ratio is 0.64, and then 0.57, and then 0.54. So the ideal is that you would cut delta x by half, you would cut the error by half, and so this is really pretty close. There is an additional term. Well, this error term here that I'm truncating. The first term is delta x to the fourth, first term in the Taylor series, times 4 factorial times the fourth derivative of delta x. So the reason this isn't exactly equal to 0.5, this ratio, is because we also have this term, and we also have all the other stuff beyond that we haven't utilized. But you can see that it's pretty close. And then we take the next step and say, okay, I'm going to use these first two terms and truncate all of this stuff. And if that's the case, then I can say that delta x, or the error, is proportional to delta x squared. I can't say what the error actually is, but I can say that the error is proportional to delta x squared. So if I cut delta x by half, then the error should be reduced by 1/4, or to 1/4. Okay, and so let's see how that works. That would be this row here. And when I go from x is 0.5 to x is 0.25, the ratio is 0.3. And then when I go from 0.5 to 0.125, it's that value, then that value. And that's the ideal value, 1/4. Okay, so you can see that it's pretty close to 0.25. It's not exactly that because there's these additional terms, but the error is essentially dominated by this by being proportional to delta x squared, the second power. Okay, so now we go and repeat it again and cut it here. So delta x is going to be proportional to the cubed, or the error will be proportional to delta x cubed. That's this row. If I cut delta x by half, then we expect the error to be reduced to 1/2 cubed, which is 1 over 8. And 1 over 8 is 0.125. So there's the value that I get, and there's 125. So you can see the ratio is pretty darn close. And then if I were to do this again, I would get a reduction in error by 1 over 16, which is is that value, and you can see that it's pretty close. Okay, so this is kind of a long process, but what I'm trying to show here is that if we use the Taylor series, we can only use a certain number of terms. We have to truncate it. And when we truncate it, the first term that we're not using is going to have delta x in it, and it'll be delta x to some power. And what we can say is that that's the first error term, and that tells us how the error will change when we change delta x.